Good morning, everybody. This presentation is the presentation I'm going to give in IEEE next week. I'm Antonio Rizza, postdoc at lab. This presentation is going to be on the mission design for the study mission, technology demonstrator for space interferometry. Before digging into the details of the mission design, let's have a brief overview on why you need to have a space interferometer. The main objective is to increase the capability of detecting exoplanets and biosignature in extrasolar worlds. This has been typically done in the last decades using indirect techniques, which means observing stellar-related phenomena to infer characteristics on an orbiting planet, mass, size, orbital period, and so on. Can be transition effects or Doppler oscillations. Transition effects essentially means through light curve inversions detecting the variation in brightness of a star when a planet passes in front of it. Doppler oscillation consists in observing the spectrum emitted by a star and measuring the Doppler effects due to the motion of the star with respect to the observer, the relative velocity of the star with respect to the observer. As you can imagine, both these techniques have a fundamental substantial drawback, which is that we can only detect, as shown here in the plot, massive bodies or bodies that are flying very close to the star. To counteract for this, we need to do direct observations, which means directly observing the planets, either the reflected light from the planet or the emitted spectrum of the planet. For Earth-like planets, we know that this peak of emissions is between the visible and near infrared. However, the main problem whenever we want to observe a planet is to be able to resolve it against the brightness of the star. So we need high contrast imaging. And this is typically solved using some occulter technique, either on ground or in space. However, the problem is that we need the occulter-based coronagraphy, which is this kind of techniques, requires very large apertures to achieve very small inner working angle, as you can see in this plot, in this video here from the Keck Observatory. The planets that are observed are at a distance from the star that is more than 20 astronomical units. How do we do this? One option is to use nulling interferometry. The idea behind nulling interferometry is shown here, a plot here on the right, and is to create an interferometric pattern such that the nulling band of the interferometry falls on the star, and we can actually see on the bright band of the interferometric pattern the planet. And here the angular resolution essentially scales as the ratio between the wavelength at which we are doing the observations and the baseline between the different segments. This is typically done on ground with large telescopes. As you can see an example here in the slides, the VLTI Observatory in Chile. Beautiful place, by the way. However, doing these observations on ground has some drawbacks because you need to cooperate with a very low signal-to-noise ratio due to atmospheric interference. So we want to bring this technology in space. A very promising concept is given by the LIFE mission concept, developed by the ETH in Zurich. And the idea is to place this swarm of 5 satellites in around L2, around the Sun-Earth L2 point. However, there are many technological challenges that are needed to be overcome in order to be able to deploy this kind of formation flying in space. And here is where STARRY comes into play. Yep. So the idea of this is a technology demonstrator funded by the NASA APRA program. We're talking about 2 CubeSats, 8 U CubeSats that are going to fly in low Earth orbit to simulate one arm of a space interferometer. And the goal is to acquire starlight from one CubeSat and reflect it to the other CubeSat using a tight coupling between a fast steering mirror mechanism and the Garage navigation and control system. This project is led by University of Michigan, the role of PI. Stanford is responsible for formation design and GNC, Garage navigation and control system design. Georgia Tech for the propulsion system, RPI for payload and fiber injection, and JPL for the system engineering part. The main requirements are highlighted here. We need to maintain a baseline separations that span between 25 meters and 175 meters. The main objectives is to, from at least a GNC perspective and a mission design perspective, is to keep an optical path difference below 0.5 meters to avoid the need in a future interferometer mission to have a delay line on board. Essentially, this means that we want the two spacecraft to operate on a plane that is always perpendicular to the star direction. And we want to guarantee these constraints for a prolonged amount of time, more than 2 orbits. And also, like, the mission has to be compatible with a lifetime duration of 6 months. So let's dig into how can we achieve that. Before entering into the details of the design, let me give you a very brief overview of absolute and relative motion preliminaries. We are going to use 2 reference frames in this discussion. One is the Earth-centered inertia reference frame, the G2000 reference frame, and the other one is the radial tangential normal frame that is centered on the spacecraft and oriented as the heel frame. We can easily, so the state representation we were going to use for both absolute and relative motions is going to be based on orbital elements. For absolute motion, we use quasi-singular orbital elements, and we can easily convert the position and velocity of the spacecraft from the ECI frame to the orbital element set. And for relative orbital motion, we're going to use quasi-singular relative orbital elements, which are given by nonlinear combinations of quasi-singular orbital elements. There are 2 major advantages in using ROEs. The first one is the dynamics becomes more linear, as can be seen in the case, for example, for circular orbits and small separations. We can write a linear mapping between the motion in RTN frame and the ROEs. And we see, and the second advantage is that we can give a easy and simple geometrical interpretation that, as we will see, will be very useful in this design of the motion in the RTN frame as a function of the ROEs. In particular, we can see that the motion in ROEs is an ellipse with a fixed orientation, whose projections in the RT and the RM plane are a function essentially of position, like the shape and orientations of these projections is a function of the ROEs. In terms of absolute orbit, we are going to select a sun-synchronous orbit for 2 reasons. One allows to have uniform illumination conditions on the orbit. The sun-synchronous orbit at an altitude of 500 kilometers. And the second reason is that, as we will see in this presentation, will allow to span for free essentially different portions of the sky and observe different directions in the sky without necessarily needing to change the relative configuration. We're going to use the LTAN instead of the relaxation of the ascending node. This is very typical for low Earth orbit mission. This essentially defines the orientation of the orbit with respect to the sun. We're going to select the terminator orbit, which corresponds to an LTAN of 6 a.m. There is one very important angle that will be very relevant for the proposed design, which is the beta angle. The beta angle describes the elevation of the star with respect to the orbital plane. And it's shown here in the picture. Sorry. Okay, so the main goal is to achieve something like this, right? We want the 2 spacecraft to operate in a plane that is perpendicular to the star direction. The starlight is acquired by one of the spacecraft and is reflected to the other. How can we do this? Let's have a look at an intuitive understanding of this. First of all, we can see that the motion of the star in RTN essentially describes a cone. A cone is a function, obviously, of these 2 angles. One is, again, the beta, the elevation of the star in the RTN plane, and the other one is this theta angle, which is the azimuth of the star in the RTN plane. Now, we want our relative motion to lie on a plane that is perpendicular to the star direction. And so, as you can see, this plane rotates in the RTN frame, rotates in the Hill frame. However, we said before, the motion of a spacecraft in RTN, at least the osculating motion of a spacecraft in RTN frame, is an ellipse with a fixed plane. So you can understand that there's no 3D solutions to this problem that can all the time lie and stay within this plane. The only solution is a degenerate solution, which essentially means a straight line that corresponds to vertical oscillations in the RTN plane at a certain desired long track separations. Essentially, the motion of the spacecraft always lie in the intersection between the plane and the TN plane. Let's see how we can derive this analytically. It's very simple. We're just imposing that the dot product between the relative spacecraft position, delta r, and the sun direction, s, is 0. And we can use the linear mapping that we showed before between ROEs and RTN coordinates to express the delta r position as a function of the relative orbital elements. And the result is that we can have an harmonic oscillation. We have this harmonic oscillation that you can see here in the slide. And this harmonic oscillation is always equal to 0 for every value of u, so for every point in time, if all these coefficients are 0. And this is achieved only if the solution for the ROEs respects these conditions here. Let's give a geometrical interpretation of this. This is saying that if the beta angle is less than 90 degrees, so if you're not observing something that is perpendicular to the orbital plane, the relative eccentricity vector is constrained to be in the origin. So delta E is equal to 0. The relative inclination vector instead is constrained to operate in this circle, whose radius essentially depends from the desired long track separations that we want to impose and the value of the beta angle. As beta increases, the radius of this circle decreases, and when beta gets to 90 degrees, this circle becomes the origin of the relative inclination plane. This motion corresponds, as I was saying before, to this oscillation here in the Artian plane. However, there is another solution. When the beta angle reaches actually 90 degrees and the relative inclination solution becomes the origin, any possible value in the relative eccentricity plane becomes a feasible solution. And this corresponds to these concentric series of ellipses in the Artian plane. However, this solution is discarded for this presentation because we want to provide a formation design that is feasible for any value, any possible value of beta. So we're not considering this possible configuration. There are some observation constraints that we need to take into account. In particular, the amplitude of the oscillation, as you can see here, depends on the magnitude of the relative inclination vector. So we may want to constrain the magnitude of the relative inclination vector as a function of the maximum amplitude of the oscillation that we want to have. Moreover, we're flying in low Earth orbit, so it's obvious that the Earth occlusion is going to be an important point if you are observing a certain inertial direction. So there may be a lower bound for beta such that we achieve a certain duty cycle. In particular, if we are at 500 kilometers altitude with a long track separation delta lambda of 100 meters, if you want to achieve less than 50% baseline oscillation, if you want to have more than 60% of duty cycle, due to the Earth exclusion angle, we need to operate at a beta angle that is larger than 45 degrees. One of the most interesting aspects of this design is that it allows an easy mapping between the formation design and the inertial direction of observations. In particular, we can see how this envelope of possible values for the relative inclination plane, each of those corresponds to a different formation design and different configurations of the formation. We can see how this envelope is mapped in the inertial sky in the plot here on the right. And as you can see, the fact that we are on a synchronous orbit that is rotating due to the drift of the right ascension of the ascending node allows us to span different portions of the sky during the lifetime of the mission. In other words, we can see the relative inclination plane as a field of view, essentially. It is pointing at the sky and is rotating with the orbit. Okay, this could be like a different interpretation of this design. One of the major drawbacks of these solutions is that this relative motion is not passively safe. Passive safety is a very important concept whenever we talk about formation design. It's a property that guarantees that the spacecraft can achieve a minimum separations even under loss of control capabilities, and for a certain amount of time at least, even under loss of control capabilities and under uncertainties in a long track direction. And this is typically manifested as a separations in the RN plane. As you can see, we don't have these conditions here. In the RN plane, the motion on the orbit is a straight line. So we need to record. So when we are on the science orbit during the science phase, we need to cooperate with this with a reactive safety mechanism, and we will talk about this in a second. However, we want to reduce at the most the amount of time that we spent in this orbit. And so to do that, we design a standby orbit that is essentially achieved by increasing the eccentricity vector in the direction of the relative inclination vector. This parallel condition between these two vectors is what enforces actually the passive safety. And so the main idea is that we can transition between one science campaign and the next one from a science orbit to the standby orbit. And an example of this transition is shown here. The radius of the standby orbit can be tuned depending on the safety margin that we want to have. So this is the general overview of the mission ConOps. The idea is that after a month from release, we acquire a certain standby orbits, and then we transition from the standby orbit to a series of science orbits. And we conceive the mission planning such that we reduce more and more during the mission lifetime the safety margin. And this is done in two ways. On one hand, we decrease the along track separations, as you can see here in the plot. We move from these relatively far away science orbits to up to science orbit that are 20 meters away. And in moving back to the science orbit, we save propellant by progressively decreasing the inclination of the standby orbit to match the amplitude of the relative inclination vector. So overall, in the science orbits, as I said before, we're going to operate under an active safety constraints and reactive safety approach, and on the standby orbit, we're going to rely on passive safety. So let's talk about transfer first, and then we're going to look at how we can actually do the station keeping in the science orbit. So one of the other advantages of using relative orbital elements is that we can find closed-form solutions for computing the necessary delta V's to go from one certain set of ROEs to a different set of ROEs. And this is exactly the way we are budgeting delta V necessary for the transfer. Here you can see an overview of the different components. And you can see what I was mentioning before in the transition from the science to the standby orbit until the very end, in which this is really needed for enforcing a certain safety margin. We are only increasing essentially the relative eccentricity vector, and we are keeping constant the relative inclination vector. And this essentially means that the inclination of the standby orbit progressively decreases and becomes rather the projection on the RM plane goes from being an ellipse to being more a circle. Okay, let's talk about the stability of the science orbit instead. Under perturbations, the equilibrium condition that we found before on the ROEs is obviously not a stable conditions. Perturbations such as J2 and drag can induce a deviation of these ROEs. So we need to compensate for this, right? However, there is a way that we can actually constrain the observation direction so that we end up in a frozen relative orbit, and at least against J2 perturbations at least. And this is done by enforcing that the delta Ix component of the relative inclination vector is equal to 0. Essentially, we are saying that the main difference between the two orbits, the chief and deputy orbit, is a difference in the right ascension of the ascending node. And so this is essentially saying that the two orbits have the same inclination, and so we'll have the same drift to J2, and so the relative effect of the Hertz-Blakeness is cancelled out. And if we do that, we see that our relative motion, if we start from ideal condition with no uncertainty and so on, it remains actually bounded, and the optical path difference remains actually bounded within the prescribed value without the need of doing any actual control. This is what the observation profile looks in terms of inertial observation that we're looking at if we select this condition. And as you can see, we are still able of mapping the entire full sky within a year. Of course, we need to take into account also for the effect of drags. So if we are not in this frozen configuration, or even if we are in this frozen configuration, we need to take into account for the effect of drags. And this can be done in different ways. We are still exploring different techniques for achieving this. The main idea is that we can either control the ROEs, so we can define control boxes around the ROEs, or we can use some direct numerical optimizations in a model predictive control framework to do that. The key message here is that we need an active control scheme, autonomous active control scheme inside the GNC to achieve this. And it's very interesting to see how the performance changes depending on different parameters that are very important from a design perspective. The differential ballistic coefficients, the difference in mass essentially between the two spacecraft, the solar flux. Here you can see a projection over the next 10 years of what the solar flux is expected to be. And as you can see, we have a peaks of the cost of station keeping whenever we are flying during the solar maximum, essentially. And obviously, the altitude at which we are operating can change the cost of station keeping. So all of these are currently trade-off parameters that we are investigating and consolidating. So to sum up, we provided a framework for designing a new generation of space-interferometry mission with a formulation that is based on relative orbital elements and allows to have a very easy and geometric interpretation of of how the design works. We provided the preliminary delta V budget. With margins, this amounts to almost 10 meters per second, which is pretty much compatible with most of the formation flying missions for CubeSats in LEO. And okay, so what's next? What comes next, right? So the main idea is that all of this has to be handled in an autonomous framework, right? And so the idea is that we are currently working on developing an autonomous GNC stack for achieving this, that is going to deploy a modular approach of different navigation and guidance and control techniques to address different navigation and control accuracy that are required in different phases of the mission. This will also encompass a certain set of fallback strategies, collision detection and escape maneuvers, FTIR role switch is very important for two reasons, both for contingency and to actually balance the ballistic coefficient so that the effect of drag is kind of compensated. And yeah, so design of the autonomous GNC system. We are planning to target two conferences this year. One is the Astronomic Specialist Conference, in which we're going to present a spin-off of this design, in which we are going to show how we can actually optimize the observation schedule, given a certain set of stars that we want to observe. How can we optimize the observation schedule to minimize the actual cost of transfer from one configuration to the other? And the other one is the ESA GNC conference in October this year, in which we're going to give an overview of the GNC design for this mission. And this concludes the presentation. If you have any questions, I'll be happy to answer.